Good afternoon, everybody. It is my great pleasure to welcome Professor Guido Mueller today from the University of Florida. Guido is one of the PIs here in the US that has been leading a big work on the optics and laser interferometry for gravitational wave observatories. He's been working for over 10 years on LIGO and the Advanced LIGO interferometer, and he's currently now spearheading activities for the Laser Interferometer Space Antenna, which is a gravitational wave observatory in space. Guido did his PhD at the University of Hanover. We actually shared the same PhD advisor, Carsten Datzman, who is the PI of the LISA mission. And well, I believe by the time I started grad school in Hanover, he was just launching his academic career here in the US. So I'm very happy to have him here. We've known each other for a long time. So without further ado, Guido, please go ahead and tell us about LISA.
Good. Thanks, Felipe. Welcome, everybody. Thanks for inviting me. It's a great place. You have no idea how beautiful this is here. Great weather, great sunshine, dry, not so humid. So throughout this talk, you will see sometimes this gator here. This is not the Florida UF athletic gator, right? We have the copyright, and we means the Dark Cosmos group at the University of Florida. So this is not our athletic gator. I heard there are some gators now here at the border of Mexico. Okay, I'm not making that joke. Is there the Rio Grande? Actually, my geography is a little bit. It's probably not more west, no more east. Okay, anyway, I'll talk about LISA. Yes, I've been working on LISA actually for more than 10 years, on LIGO for 20 years by now. That just means that I'm much older than Felipe. And we built big parts of that, but it's all history. I will talk about LISA and what hopefully becomes the future, or what looks like now that it becomes the future. Right? We are on very solid ground with LISA these days. I will start talking first about gravitational wave sources, frequencies, amplitudes. Very briefly, how gravitational waves measured. It's an optics place here, right? So I typically tell the astronomers how laser interferometry works, so these two sine waves and stuff like this, but it's an optics place, right? I don't have to talk about micro interferometry here. I'll very briefly go over this. I will talk about the sources of LISA, and then a little bit how LISA works, and then the status of the project. Where are we right now? What is going on in LISA? And hopefully I can convince everybody that LISA is becoming real faster than sometimes we like, because there's a lot of pressure right now getting all the designs together and coordinating all the activities. But first, let's talk about gravitational waves. Very brief. Gravitation. Since Einstein, we know that gravitation is actually not a force. It is curved space-time. John Wheeler had these famous sentences: mass tells space-time how to curve, space-time tells mass how to move. And if you have two masses moving around some curved space-time or creating curvature in space-time, you immediately see that actually this must create some ripples in space-time that are actually propagating outwards. And gravitational waves are essentially nothing else than the messengers of changes in space-time, very similar to electromagnetic waves, which tell you about moving charges at the end of the day, where they come from. That's a source of electromagnetic waves, and gravitational waves tell you something about moving masses. Einstein's field equation, you can start working with that and linearize this, and I would actually have to look into a textbook to do that myself, so ignore that for a while. The key part here is actually this small factor, big G over the force power of c, and we see that in a second again. Very briefly, what do gravitational waves do? And I'm sure you have seen that. Gravitational waves, when they come in, they actually change distances. So here we have two gravitational waves propagating into the board or coming out of the board. It doesn't really matter right now. Going into the board, and then along the x and y axis they squeeze and stretch the distances. So the circle will turn an ellipse, circle again, ellipse, circle again, and then we start from the front again. And you can do this along your coordinate axis, or you can do that under 45 degrees. And these are the two polarizations we have in gravitational waves. Right, so you have plus polarization, cross polarization. Depends on the definition of your coordinate system with respect to that. So what do? They change distances. They change distances differentially. The letter that is used for gravitational waves is h. Nothing to do with Planck. Right? This is h, strain. It's a relative length change, so delta L, the length change you measure, depends on the amplitude of the gravitational wave measured in strain times the overall distance, at least in the limit where the wavelength of the gravitational wave is long to the distance. We don't start averaging things out. And obviously, you know that when we want to measure differential length changes, interferometry is a tool we all are familiar with and we all want to use for this because it's the most sensitive way to measure differential length changes. Short primer, gravitational waves. So the amplitude, when you calculate that from general relativity, is 2 times big G over the fourth power of C. The first thing you learn in physics is that big G is actually a very small number, right? Your mechanics 101 class, probably in high school, that's the first big constant you come up with, and it starts with 10 to the minus 11, and you wonder at high school, 10 to the minus 11, what does that actually mean? It's a very, very small number, and you all know that the speed of light down here is a very large number. So the fourth power makes it really small, what's standing in front of this factor here. And the distance to your sources in astronomy is typically also a large number. So this prefactor here is typically in the order of very, very small. So to get gravitational waves, measurable gravitational waves, you need a large mass quadrupole moment, and this is the acceleration of the mass quadrupole moment, or the second time derivative of the mass quadrupole moment. This number better be very, very large. So the sources we're talking about for gravitational waves are all astrophysical sources. Black holes, neutron stars, trying to generate measurable gravitational waves on Earth with some steel frames or whatever is pretty much hopeless. I mean, you can easily generate them. I can generate gravitational waves. Here, a couple, right? No chance to measure any of those. Now, for mechanics classes, I sometimes let them actually calculate the second time derivative of the mass quadrupole moments for binary systems. Then I throw the Schwarzschild equation in there. And then you can actually derive for circular orbits that the amplitude is more or less the product of the Schwarzschild radii of the 2 orbiting bodies. Right? So the ideal source is a binary system, 2 black holes, 2 neutron stars orbiting around each other. Each of them has a Schwarzschild radius, right? Gm over c squared. And then you can calculate the Schwarzschild radii of the 2 masses. That product divided by the distance from the source to your detector is actually a very good approximation for the amplitude of gravitational waves. So next time you sit in a bar and somebody next to you wants to ask you about gravitational waves, this is kind of very impressive if you can derive this by hand this way. And the numbers you get out there is on the order of 10 to the minus 24, 10 to the minus 21, depending how far they are away, how big they are. This is kind of the ballpark number for what you want to detect. Frequencies. For frequencies, you can also use Kepler, because for most of the time they are pretty much Keplerian orbits, and then when we're getting closer and closer, that way, that's when we get some general relativity distortions in there. But the basic frequencies are on the order of kilohertz if the central mass is on the order of solar masses. And if it gets heavier and heavier, the frequencies drop down, mostly because their Schwarzschild radii become larger and larger, and when they start to collide and meet each other, then it's over, then they start to merge, and the collision is done, essentially. That tells you the upper frequencies. This is orders of magnitude. So for 30 solar mass black holes, the typical LIGO signals, you will get upper frequencies just before merge of a few hundred. But if you think about that, the entire inspire is actually measured. So this kind of gives you an idea of the frequency range that we actually see in LIGO. And then later on in LISA, where the masses become much larger. Mentioned LIGO already. Yes, I worked on LIGO. We built the input optics for LIGO, large portions of this. The detector. The optical design actually comes out of Florida. But nobody talks about this anymore. This is all history these days. So LIGO had, as you know, or Advanced LIGO should say, together later with VIRGO, 3 science runs. We're actually in the middle of the 3rd one. The first science run, Advanced LIGO, started in September. We had the famous discovery. That was actually interesting. At that time, I was at ESTEC in the Netherlands, the ESA Technology Center, and we had a meeting in a famous group called the GOAT, G-O-A-T. Somebody at ESA made fun of this when they came up with this acronym. And we had people in the room that actually said, hey, what do you want with LISA, with gravitational waves? LIGO has never seen anything. This will never, ever work, essentially. And I was sitting there with Bernie Schutz, who was also in the LISA group and the LIGO community. We got the email, hey, there's a detection. Then the guy next morning talked, LIGO will never ever work, never ever see anything. And we were sitting there and we're not allowed to say a damn word about that event. Okay, a couple of months later, somebody stood up in that room and said, did you hear nothing about that detection? Everybody knows that already. That was way before we had the press conference. There was somebody in Arizona, I'm not talking about that. Okay, 01 here had a couple of detections, 02, a couple more, so 10 black hole and 1 neutron star merger in that time frame. And then 03 started, part 1 started in April, ended 1st of October. So this is half a year. Half a year is 26 weeks. We have 33 candidate events. 33 candidate events means there are 33 events in there where we are very, very certain these are actually gravitational waves sources. So that is 1 per week, right? So going from none over many, many, well, the entire time of the universe to 1 here and now 1 per week here tells you how powerful these instruments can be and how fast we actually gain. And the secret here is this 1 over r here, right? In contrast to telescopes, where you measure power, we are measuring amplitude. Right? So if we double the distance, the reach, the event rate goes up by a factor 8. Right? And that's what this 1 over r is doing for us. That's what we gain so fast, and that's where I got to 1 per week here. Part 2 just started. The Japanese Kaga system will join soon, hopefully. Then we get better and better sky localizations. And Advanced LIGO Plus also just got approved, or take the just out, it was I think in February, March. And the goal there is to have 7 times larger reach than Advanced LIGO now, supposed to come online 2024, right? You're involved there. I'm not really involved in LIGO anymore. And 7 times larger reach, 7 cubed is, oh, that's a big number, 49, 50, 350. So 350 events per week, roughly speaking, is what you could expect with Advanced LIGO Plus. And it pushes to lower frequencies. So you're talking about gravitational events 10 per day coming out there. Right? And then you can ask yourself, why space, right? Why do we actually put money into space and go to space and detect actually gravitational waves with a different method? There's a different detector, which is probably not going to be cheaper. Space, right? Can't be. And the answer is the same you get from astronomers, right? We have this beautiful night sky here, right? Optical system, visible light. You can do fantastic astronomy here with visible light, but you want to go to infrared too and other wavelengths that you can't observe here. We have the same problem in gravitational waves. So LIGO is measuring in the audio band 1 hertz to 10 kilohertz. Actually, LIGO is probably right now about 20, 25 hertz as the lowest frequencies. Pushing hard, the folks are working hard to get to lower and lower frequencies, but somewhere here is what we call a brick wall, what we call gravity gradient noise or Newtonian noise. And the problem is if you do interferometry and you want to see small length changes between 2 masses that are isolated from the rest of the world, the only thing you can't isolate is gravity itself. And that means that any gravitational field changes in here will certainly push and pull on these masses. And at the end of the day, this is something that will put limits on these detectors on the ground. Right? There are air currents, wind, right? Pressure changes, there are seismic waves, whatever. There are tons of things that are floating around here that will pull and push on these masses and move them around. So the force noise, acceleration noise we're typically dealing with, forces of accelerations of 10 to the minus 15 meters per second squared per root hertz, roughly 10 to the minus 15 meters per second squared. That's a fly flying by a meter away, or that's an E. coli bacteria sitting on the Mars, that weight. So you can see that we are talking about very, very small forces that push and pull the masses around, and here on Earth the environment is just too noisy. So we'll be limited on ground to masses in the order of 100 solar masses, maybe a few hundred solar masses. Who knows where the real border here is? But at one point it will come, and that's why we need to go to space. That's why we want to detect gravitational waves, actually for LISA in the 10 microhertz to 1 hertz range, or in the mass range, roughly 1 million solar mass, typically mass scale for LISA sources. So what do we know about sources here? What do we expect in sources here at the low frequency end? Here you see the sensitivity curve of LISA. It's actually the characteristic strain sensitivity of LISA, 10 to the minus 20, 10 to the minus 21 here. Characteristic strain sensitivity means it's a linear spectral density. So strain per root hertz times the square root of the measurement frequency. That is kind of the way to fudge in the different integration times for the different signals. There's no real good curve here which you capture for all signals. That's the reason why you very often see here characteristic strain, linear spectral density, or a strain integrated over certain measurement times, and so on. So you see all types of different numbers here. It's very difficult to actually truly compare them unless you really know what the source and what was done with them here. So this characteristic strain here, and here we see a bunch of signals coming in there, and here we see the frequency. So here at about 3-4 millihertz, that's where the sweet spot is. So let's talk about the individual signals. These big ones here are our massive black hole mergers. Mass ranges 10 to the 4 to 10 to the 8 solar masses are the ones we actually should be able to observe. This is what we call a waterfall plot. So here you see the mass. Here you see the redshift. Ionization is somewhere here, right? So we stopped watching somewhere in this range here. And we see black hole mergers out to very, very large redshifts deep into the universe. We don't really know if they exist here, right? This is actually what LISA is about. What is the history of massive black holes? What is the history of 10 to the 4, 10 to the 8 solar mass black holes? We see a merger candidate, 10 to the 6 solar masses that we see out to redshifts of 20 with pretty large 20 signal-to-noise ratios. So signal-to-noise ratios you see for the top LIGO events, 20, 30 here. Here we get them out to very high redshifts, and then signal-to-noise ratios of a couple thousand when they're actually within a few gigaparsecs within redshift of 1 or 2. This is one of the major goals of LISA. These signals here, they chirp in, they spiral into each other slowly, emit gravitational waves. That's the energy loss mechanism, and then we start to see the acceleration of that and the merger phase here with very high signal-to-noise ratios. Another signal are into extreme mass ratio in spirals, right? So in initial physics classes, you often talk about test particles, test masses, a test charge, probing the electromagnetic field or electric field, and so on. So here we have a 10 to 100 solar mass test particle, right? That's what we call test particle in this field. And it orbits around 10 to the 6 to 10 to the 8 solar mass black hole. And these are the black holes you find in virtually all galaxies as far as we know. When I say we, that means I'm just referring to astronomers who tell me that this is the case, because I don't know personally. They tell me that. But if you do that, if you look at these here, if you model these, and if they have some angular momentum and some spins, which they typically have, you get actually very complicated trajectories, orbits out there, where the interaction between the angular momentum and the spins creates these type of orbits and time evolutions here. And this would be a very, very interesting source to detect and to measure and to check if we actually really understand the dynamics in general relativity, dynamics in the high curvature, in spaces which are highly curved. Here, very interesting source. We expect to see several of those. Here you see the signal to noise here down here. We have compact galactic binaries, 100,000 signals in our own galaxies that we expect. So these are white dwarf and neutron star binaries, mostly white dwarf binary systems. There's supposed to be several hundred millions of them in our galaxy. Supposed to be 100,000, 200, 300,000. We don't really know. Orbiting around each other at frequencies which LISA will actually be sensitive to. And somewhere here we expect actually to be limited by gravitational wave noise. Right, that we have broadband emission of gravitational waves that we can't resolve in frequency space here, and they would be a background signal which will be modulated by the annual motion of the LISA detector. Sometimes it will face its galactic center, sometimes it will point away from it, and that will modulate the intensity, and we can do some statistics with this. So for some people this is signal, and for some people this is noise in the detector, but these are guaranteed sources that we have in LISA. And then It seems to be that this is the best range for surprises because of the mass range and the sensitivity and the lifetimes of these orbits. We'll see what you see on top of this. People have called this the holy grail of gravitational wave astronomy. That is a frequency band where we expect the most science coming out there, most different signals and diverse sources. So my colleagues put this all together into some plot that kind of looked like this, and they turned it into mission requirements, and each of these lines is a very specific mission requirement associated with a scientific goal that they have, and no surprise, they actually really trace out the sensitivity curve that we gave them up front. Right? This is a detector we can build. Give us a mission requirement that matches to that. That's how it really works, right? There's no point to put something down here because you have no clue how to measure that. In this particular case, it would be probably hidden by the galactic binary background anyway. So these define our mission requirements, and we can use this now here to defend our mission requirements, science requirements, against budget cuts in ESA and NASA, which will at one point maybe come and try to push this up, and then we can tell them, hey, we lose this science and that science and so on, so please give us more money. But this one here has turned into technical requirements. First one is acceleration noise, so how quiet do the endpoints of our interferometer have to be? This acceleration noise requirement 3 times 10 to the minus 15 meters per second squared per root hertz is actually pretty similar to the acceleration noise that we have in LIGO, except that the frequencies are much, much lower. And you see here the frequency shaping here. So at low frequencies, 400 microhertz, we relax the requirements a bit. At high frequencies, we relax the requirements a little bit because at high frequencies, we will be limited by displacement noise or sensor noise. So displacement noise that some of our components change their distances, or sensor noise that our sensors, for example, short noise limit, doesn't allow us to be much better than this. And the limit here for displacement noise is 10 picometers per root hertz. So 10 picometers on LIGO scales is gigantic. Right? On LIGO scales, LIGO is measuring 10 to the minus 18 meters typically, 10 to the minus 19 meters, right? Short-lived signals. So this is gigantic for this, but LIGO is doing this at 400 hertz. We have to do it at millihertz. LIGO, the absolute distance between the mirrors in LIGO is stabilized actively to a few picometers over the 4-kilometer distance. Now we have to measure the changes at 10 picometer level in space. So interferometrically, this is not really the greatest challenge, right? So if you have a good vacuum chamber, good temperature stability, a piece of ULE or zero Dewar, you get that fairly fast, actually. But the tricky part is in the details of the mission. Frequency range, our requirement is 100 microhertz to 0.1 hertz. And you say sometimes the goal, 20 microhertz to 1 hertz. So what's the difference between the goal and requirement? So we have scientifically essentially really a requirement that we want to be able to detect gravitational waves here. So the mission, the project is not allowed to put anything in there which jeopardizes detections at these frequencies. But we are not required to test down to these frequencies. So testing has to cover this frequency range. This here can be bridged by modeling. And the reason is that if you want to test at 20 microhertz or 10 microhertz, these are several weeks of measurements of every different change you're making. Right? You're driving the cost up if you really would start measuring here at these low frequencies. So we have to stop that somewhere, but there should be nothing built into the system that actually stops us from measuring gravitational waves here. That's the difference between requirement and goal, and we always discuss what the meaning of these works really are, but that's the basic idea here. Okay, so we're trying to get down to essentially 10 microhertz. There. Okay, how does LISA look like and work? LISA are 3 identical spacecraft in heliocentric orbits. So I think it was Pete Bender or Jim Fowler in the 70s already found some orbits around the sun, heliocentric orbits that were trailing Earth, that were tilted against the ecliptic, 60 degrees, against the ecliptic, that cartwheel around the sun, where the triangle that they form here stays fairly stable. The constellation essentially doesn't fall apart. And these are the typical LISA orbits we're talking about. So in the past, we had 5 million kilometer arm lengths. Now we are down to 2.5 million kilometers, so half of this. We are sitting at 20 degrees. There were initial designs, or in between designs of 10 degrees, but right now we're carrying 20 degrees out there. Inclination with respect to the eclipse is 60 degrees. So 2.5 million kilometers means 8-second light travel time between the spacecraft. So these are our endpoints of the interferometer. The round trip time for LaserCom, 433 seconds, was on the ESA tables. I'm not sure if they don't understand that this is actually range, but somewhere we are sitting here at 430 seconds communication. So commissioning of that instrument here will be a tour de force. Right? You send a command in, then you go and sleep, and then you come back, essentially, and then you see what came out of it. So this will be better works, and we have a lot of intelligence on the spacecraft here, and so on and so forth. I come to these things here in a second. Mission phases, I stole this here from LISA, unclassified, just to make sure somebody from ESA and NASA is watching. So here we have the launch stack, we have the 3 satellites, and they are separated, and then they have their own propulsion module, and we're brought then into this constellation. There's a cruise phase of about a year built in. You see here the trapezoidal forms, shapes of these satellites. Old ones and maybe other ones will have cylindrical shapes. There's a discussion going on what is better right now. The cylinders look nicer historically to us, right? These tuna cans. The problem of that is if you stack them up in a rocket and you launch that, the lowest one has to carry the weight of the other ones, which essentially means you have different mechanical designs, or you have to have some spacers in between that doesn't transfer the load. And that was a concern, and that's why they started thinking about these shapes and forms. So I will see where this is going at the end of the day. Not particularly important right now. So you will see the drawings here mostly with these cylindrical shapes, these tuna cans. We are kind of used to those because that's a shape we had for 20 years, and the other one is just coming now here. So here you see essentially the constellation. We have here 2 identical optical systems here. I'll talk about them in a second. They send light out. Here are the famous LISA telescopes, 30 centimeter telescopes. They are send and receive telescopes. You send one laser beam in this direction. Once the laser beam is at the other spacecraft, 2.5 million kilometers away, 30 centimeter telescope will be a 10 kilometer beam size. And the 30 centimeter telescope is cutting out a small fraction of that beam and measures this here against the local beam and sends the local beam back to the first spacecraft. You have 2 of these assemblies on each of these spacecrafts. And here the yellow boxes here, these are our test masses. These are the free-falling test mass I will talk about at the end a little bit. Philippe knows more about this because he worked on Pathfinder, and I didn't. Okay, so as our free-falling test mass in each spacecraft, these are the endpoints of our interferometer. See this constellation. If you zoom in there, here we see here 2 optical benches. The ULE or zero Duo, most likely zero Duo optical benches with hydroxide bonded mirrors on there, not only 5. If you follow the beam lines here, they don't make real sense here. And just cartoonish, the real optical bench has about 60 components on it. Here, and so they do a local interferometer. We'll measure the distance between the test mass here and the optical bench. So this is a free-falling test mass. This is the one that's inside the spacecraft, and the spacecraft is steered around this test mass. We do interferometry between the test mass and the optical bench, and then we do interferometry between this optical bench and the optical bench 2.5 million kilometers away. And then the same interferometry at the other end, and then we have 3 interferometer signals. And then we can give it to an undergrad student or high schooler here, add the 3 numbers or subtract the 3 numbers, and you get your length changes. Okay, so that is the easy part of that entire part. Then we have here backlink interferometer, right? So in a normal interferometer, we have beam splitters where we split the beam with some piece of glass, right? And I know you know more about glass than I will ever learn here in this place. Split is a piece of glass. The problem is, because of the dynamics here, and I'll talk about this in a second, we can't have a fixed angle between them because the angles are breathing. And that's why we have two benches here, and they will be steered here, and the link will be done with a fiber, with an optical fiber here in both directions. And the phase noise in the fiber is common in this and in this direction. That way we can build an artificial beam splitter for LISA. Transmitted light to what's coming out, received, once we cut out this small portion of this big beam, we receive 700 picowatts. That gives us a short noise limit of roughly 2 picometers per root hertz. You will see different numbers here in different talks and different papers and so on, because this might be the limit for one link here, where we shoot the laser beam over there and just look at the short noise of one link, or we should look at the short noise of both links, so in full arm, or we look at the short noise of the full constellation. So there are different numbers floating around. That all have to do is what do we actually really mean here with short noise. Here. And the interferometers here are all heterodyne interferometers, so we always have laser beat signals. We measure the beat signal at about somewhere between 8 and 25 megahertz, and then we follow the phase, measure the phase evolution of that beat signal sorry, against a local ultra-stable oscillator, which is a fancy word for a clock. Okay, so measure beat signal, I have beat signals against the clock, and this is actually our signal then. Here we see an old picture. It says Astrium, so this is the initial early LISA version that changed to Airbus now. Here, where we have the test mass, here at the end, then the optical bench is actually vertical with the beam line. Here's the interferometry to the proof mass or test mass, proof mass, both acronyms. And then we have the beam coming out and then sent to the telescope, expanded in this mirror here. Here's a primary mirror of the telescope, sent over there, and then we have a copy of this on the other side. And then we have 3 of those, so each pair here is sitting in a single spacecraft here, right? And the breathing angle I was talking about, due to the long arm constellation, due to changes in the gravitational field, due to, for example, Earth's presence, changes the local gravitational field where the spacecraft are moving in, we actually see angle changes in the constellation. So it's not a stable, ultra-stable interferometer like we have in LIGO, but the angles are breathing by, actually this should be now plus minus 0.5 degrees. This is kind of the conservative limit we are carrying around, but the real orbit is probably a little bit smaller than that, so plus minus half a degree. Still, with the small divergence angle of the beam, you will have to track the motion of the far spacecraft. So we have to have a breathing angle here. We have to change the angle by a rate of 5 nanoradians per second. If you do picometer interferometry, nanoradians should scare you. Right? And these motions are critical. There. It's a dynamic interferometer, if you want, compared to LIGO, where everything is as fixed as possible. So here's an old drawing. There's the 2 parts here. These are cylinders here that are thermal shields to keep the temperature of the payload inside these tubes here stable. So here we have a test mass, this optical bench, telescope would be here. We call this a MOSA, moving optical subassembly. It's sitting in the LISA core assembly, right? So if you learn something about space agencies, they're really good in acronyms, right? So really, really good in acronyms, and I think that's a defense mechanism there by now, that it makes it very, very hard to get actually into this business. So you have a very long list of acronyms, and then the people changing it. So these 2 MOSAs will be actually changing the opening angle to track the other spacecraft here. You have launch logs and so on. This is a cartoon drawing of this, early drawing of this, how this is supposed to work. I am not allowed to show you the detailed design, sorry, non-disclosure agreements and stuff like this. I don't even have them on the laptop because there's a danger that I put them in the talk at one point. Here's another toy model of this GRS system. This will be the optical bench. This shiny area here is a clear, stay clear zone for the telescope. And this would be a toy model of a telescope here, light in, primary here, off-axis telescope, 30 centimeter diameter. Actually, the mirror right now is probably 37 centimeter clear aperture because of some adjustments we made for dealing tilt-to-length couplings. This is a sequence here. The real design is much more complicated than that. With all the optics in it. And that gives you an idea what the core components are. Gravitational reference sensor here. This is where the test mass lives inside this vacuum tank. Optical bench. the brain of the instrument. That's where the interferometer is happening. That's where the beats are. The laser beams are superimposed, are separated, split up, and so on. And then here's a telescope, beef up the beam. Send it to the fast spacecraft. So we talked about the breathing angle here, right? We have that. The spacecraft, the breathing angle has, and also this angle here has effects that could actually affect our sensitivity. So, for example, we have the free-falling test masses in here, and we steer the spacecraft around it. And the spacecraft in this process jitters around the test mass with angular fluctuation in the range of 10 nanoradians per root hertz. This is the values we know from Pathfinder. So there's kind of jittering here. And if you have any additional misalignment in the system or wavefront error coming from the not perfect telescope, then you actually start probing this rough wavefront on the far end. Or you're coupling through some geometric errors here, pupil mislocations, misalignments between the optical bench and telescope in there. You get a apparent length change from this oscillation still to length coupling. This is one of the big things we are fighting right now. So wavefront error we have right now is 30 nanometers. Details are TBD. Right, you know a lot about optics. Right, just 30 nanometer wavefront error doesn't really mean anything, right? Is it RMS? What's the spatial frequency? And all these other things, right? These are the details we are trying to work out right now. What Zernike polynomials are critical, or should be expressed as in spatial frequencies, and so on. We're getting closer and closer to solving that, but then we have to also get it built, and this is a fairly fast telescope. It makes it a little nasty to build this. Another thing we are talking about, we have problems with, and that's the arm length variation. Right? Because of the Earth's gravitational field, or generically even without that, because of the orbits, we have arm length variations. So it's not only the longest interferometer we might ever build. Okay, that depends on definition of interferometer, Voyager and things like that. Right? But it's a very long interferometer, definitely. It's definitely one with a very long arm length difference. And the arm length will vary by 35,000 kilometers plus and minus over the course of the year. And that means we have speeds, relative velocities between the spacecraft in the order of 8 to 10 meters per second. And we want to see now picometer changes in this 10 meter second signal. Now, this one here creates a Doppler shift of 10 megahertz, or if it's 8 meters, it's 8 megahertz. That's the beauty of using infrared light, right? 1 micrometer light gives you 1 meter per second is 1 megahertz Doppler shift. So we receive here Doppler beat node here for 10 megahertz, let's say, and we are looking at phase modulation in this 10 megahertz signal. That's the signal we are actually after. So it's a highly dynamic interferometer in principle, although all the dynamics are happening on the annual scale, frequencies 1 over a year. While the signals we are using at 1 over a day, 1 over a few days type of frequencies here, right? But because the arm length is so different here, we know that laser phase noise will actually enter it, right? You know, Michel's interferometer, equal arm Michel's interferometer is immune against laser frequency noise or laser phase noise. This context is the same. LIGO interferometer are not really equal arm lengths. They have a 40 centimeter arm length difference in there, but they're pushed more closer to equal arm lengths. And then they stabilize the laser frequency to the instrument to suppress laser frequency noise. And we can't really do that. We can't really lock the laser to the arms. Actually, we can. We have done that too in a mock-up, but it's not really what we want to do. It's very tricky. But we can. So we are sensitive to laser phase noise here, and solution here is that the same phase noise is actually measured at the various locations multiple times in different linear combinations. And so here you see a signal S12 that will be measured here at the mother spacecraft. So here's a 2-arm version of it at one spacecraft, and S13 is measured here. And these are the phase noises of the lasers. Phase noise phi 1 of t, phi 1 of t. So it's the same laser here feeds these two. Then it would be identical here. And then the receive phase, this is setting up in a transponder scheme. So you measure the phaser coming in here, lock a laser to it, and send a copy back here. And you get the phase of these two lasers, of this laser here, time delayed by the round trip time. And then you form a linear combination of these data streams, and the laser phase noise disappears. That's called laser time delay interferometry. essentially an algorithm that allows you, if you measure the phase multiple times, to subtract laser phase noise. And we have to do that by a few orders of magnitude, 7, 8, 10, so the typical numbers. And we did this actually in Florida now 8, 10 years ago, where we simulated the light travel time electronically, then regenerated laser beat signals, and were able to suppress the laser frequency noise by many orders of magnitude. So this is a laser frequency noise of a pre-stabilized laser, somewhere in the 100 hertz per root hertz range, something that values we actually have in LISA, expect in LISA, fairly robust system. And then we can subtract the laser frequency noise in this process to meet down here the 20 picometer per root roughly requirements that we have at this moment for the constellation here. Fairly easily in higher frequencies, and here's a little bit of additional noise in there. JPL has done similar measurements without the time delay. This actually works quite well. And phase closure in astronomy, in gigahertz astronomy, terahertz astronomy, they have done the similar things here to suppress phase noise here. So this is working quite well. So this is then the system here. But what we need for this here to work is knowledge of the distance. So we need to shift essentially these data streams by certain amounts of time. And these times have to be known fairly well, very well. And that means we need the knowledge of the light travel time or signal travel time between the spacecraft. So we need a ranging system. The requirements of the ranging system are we need to know the position of the spacecraft within a meter, 30 centimeters, maybe 10 centimeters. And we are doing this with PIN codes. Talk about this in a second. We need accurate time stamping, obviously. And because all the beat nodes are measured at the various spacecraft against local clocks, we also need to measure the noise, the relative noise between these clocks. So having two clocks, there's noise between them. That is phase noise in our signal. We need to measure the phase noise of that. And we do this by exchanging phase information of the clocks as well. So here you see a little bit of a spectrum that is actually on the laser beam. So it's not only the carrier that you see here in the center that is doing the interferometry. We have also a couple of sidebands or band of sidebands generated by a pseudo-random noise code that is modulated on the laser phase. The pseudo-random noise code is kind of a band of a megahertz, is bidirectional, goes in both directions here. Manchester encoded that it's orthogonal and all that other stuff here that we know from the CIA or somebody else or something like this, right? And it's bidirectional and allows us to measure the distance here between these within a fraction of a centimeter if we need to. And it's also good enough to synchronize the clocks here. So PIN code, the switching here of the phase is well timed, essentially allows us to synchronize the clocks. And then the phase noise of the clocks is encoded in gigahertz sidebands, 2 gigahertz here, 2 gigahertz plus 1 megahertz here. That is linked to the ultra-stable oscillator, up-converted from the USO. And then we measure the differential clock noise at both of these locations. And these signals also go in the time delay interferometry combinations. So the simple version of this that we had here, that is actually way too simple. There are about 20 more terms here that need to get into the system to subtract all these various noise sources in LISA. This is obviously the leading one. Everything else gives us a last order of magnitude. So there's a problem in these other 10 terms that we are off by a factor 2, estimating how well we can do it. It's a very graceful degradation. The laser frequency noise, this one here, this is the big stuff here, okay, where we have to get to. So all this is needed for time delay interferometry and retires in some way the sensing requirements that we have to deal with here. And so it gives us a capability to measure the distance between the test masses down to a few picometers per root hertz there. Now the displacement noise requirements include also length changes within the interferometer test bed that are not coming from the sensors. They are not sensing noise, but are really true length changes. Right, and there were two things. One is the optical bench. So components on the optical bench have to have picometer stability relative to each other. And then the beam expanding telescope, because it's a reflecting telescope here, the distance of the within the telescope enters into the measurement, and the secondary and primary distance is changing. That looks like a gravitational wave. So this telescope and the optical bench will be made from materials you're very familiar with, right? Low CTE materials, zero Dür most likely. ULE is an alternative maybe for the telescope. Zero Dür will probably not be used from the telescope because the telescope comes from the United States, and the Europeans want to use zero Dür. As an alternative here, CTEs, you know, in the order of 10 parts per billion per Kelvin here, and then you have a temperature requirement, stability requirement of about 100 microkelvin per root hertz in the LISA band, and that gives you at least the nominal stability on the optical bench and within the telescope. But then there are challenges. One is to reach that stability, and the other one is mounting of these components. Right, if you start mounting these components in metal pieces, right, because glass breaks, and if you wouldn't have to put it on a rocket, it would be great, but we have to at one point. So there will be mounts between glass and titanium or something like that, right? And then you have the different CTEs, and that can deform the mirrors. You get back to wavefront errors and things like this. So these are the discussions many of you are probably much more familiar with than I am. Right, where you have mounting problems with mirrors essentially in spacecrafts. There. This will be one of the typical challenges I think we will really have, how to do that correctly. In Florida, we are setting up for testing the stability of the telescope. So this is a small type mock-up. We play a little bit around with ULE structures and so on, and you know, full ULE piece like this, monolithic ULE piece, that would cost a lot of money. So we put this together and screw it actually with screws together, ULE plates, which makes it cheaper, not that cheap, unfortunately. And that way we got actually, including with these metal screws in there, stabilities of around 100 femtometers and below here per root hertz over the LISA band down to 10 to the minus 4 hertz. And the idea is that once we have figured out how to do this correctly and best here, then build a larger system where we can drop the LISA telescope in and then run the laser beam through the telescope, which reflect it and measure then the length stability of the telescope in such a structure. We need to do this interferometrically to get to picometers, and so this is kind of a way to do this. That kind of results from our proto-GSE system. And we just got the award notification from NASA that we will be funded for developing this over the next 2 years to build this test bed for the telescope and a couple other gadgets essentially, and Philippe is part of this here. Right, so results from the proto-GSE. Verification will be a big challenge of LISA. Ground verification of a system like this is tricky. I haven't talked much about the gravitational reference sensor yet, so I will switch gears now and get to that one here. The stillest place in the universe, I stole this from Carsten Dunsman. I would have said the quietest place in the universe, but stillest sounds really cool. It's more sensitive than the weight of a virus. That's what he said, and that's what is true. So the idea of LISA Pathfinder was that we shrink the 2.5 million kilometer, or it was at that time 5 million kilometer, to 38 centimeters to demonstrate free fall in LISA. So you have here two test masses, cubic test masses here, and the goal was to put these two cubic test masses into free fall and steer the spacecraft around it. This technique is called drag-free technology. We call our system a gravitational reference sensor. Others would call it an inertial sensor. We don't do that because then we get ITAR problems. Oh, it's on tape, right? Okay, sorry. So it's a gravitational reference sensor, and the systems that have flown before had all sensitivities that were in the order of a factor 1,000 to 10,000 to 100,000 worse than what we need in LISA. And that step was essentially the one where the space agencies were really concerned, can we do that? The main reason for that additional noise was probably that these test masses have to be discharged. In the old times, they used a little gold wire coiled around that went to ground, spacecraft ground, to discharge the test masses, and that increased the mechanical coupling between the spacecraft and the test mass and started shaking it around. And that was a limitation of the old systems, is my understanding, and these days we are actually using UV discharging systems for discharging these cubes, and that way it can mechanically be completely isolated from the spacecraft. And that we only have electrostatic interactions between the spacecraft and the test mass, and also gravitational interactions, obviously, also on top of this. So the idea of drag-free is actually pretty old, comes from the 1960s, and LISA is doing this only along one axis per test mass, right? If somebody tells you we have two test masses and we steer spacecraft around single spacecraft around both test masses at the same time, that doesn't work. So you can only do this within one axis per spacecraft here, and you have to control all other degrees of freedom electrostatically. And test the picometer interferometry. Here are a couple of nice pictures from this. So here's the optical bench for LISA Pathfinder. It's about 30% the size of a typical LISA optical bench. So it's fairly small, piece of zero-dur with hydroxide bonded optics on it. So the angles here are all within 10 microradian of the nominal angles. So it's very well polished and then bonded, precision located here on these things at the University of Glasgow, and then interferometrically read out. Here are a couple of mock-up test masses. You know that better than I do, right? So this is a test bench here. LISA, as I said, is about, 4 times the size, roughly speaking. And that was then put on a rocket inside the system here. So here's the 2 vacuum cans with the test masses in there. So the 2 cubes are in here. I'm done? Okay. 2 cubes are in here. So they are sitting inside these vacuum cans here. Optical bench is sitting in between. The rest is supply stuff. Lasers, power supplies, and what else, computers, what else you need. And then it put on a rocket, launched in December 2015. It would have been a real highlight in the year 2016. The results would have been a great highlight for the gravitational wave community and for astronomers and so on. But you had a problem because LIGO beat that, right? So we had LIGO detection in September. We announced it in February 2016. These guys started launching in 2015. And in March, we got the first results in that I was allowed to see. I'm not sure if they were public at that time. In March, and that beast meet the requirements out of the box. So it was a great year, great couple of months to get LISA out of the gates, essentially, and actually get it funded and get it going. Here's a paper, the first paper, somewhere here, right? Felipe, that's you, right? You won't see me in here. I had nothing to do with that project, right? I don't want to take any credit, right? I was here and there a little bit involved in an occasional review somewhere that I'm not supposed to talk about. But other than that, here, I have nothing to do with that. Right? Felipe, great job. As a great group who did this. And these are actually the bad results. The real good results came out months later, once they had actually the commissioning done. Pathfinder had the goal of demonstrating LISA requirements times a factor 10. So it was supposed to be factor 10 worse than LISA. There was supposed to be then another iteration of lessons learned to get to the LISA requirement. Once they were done, they were well below the LISA requirement. I believe this is the only space mission that we ever flew which exceeded all requirements by a factor 20 to 30. I don't know if there's any other space mission out there that did that. So they paved the way for LISA together with the scientific pressure coming after the LIGO detection. So this is a fantastic news, and after that, we just submitted a proposal, and Carsten had time until Monday, but Friday 13th, it sounds just too good to pass it on, to pass over it, and so he submitted it Friday 13th in January 2017, after all this came in there. He worked on that document. We had 300 members in its consortium, 2017. This one, the core team here. We're now well over 1,000. We were selected in June by ESA Science Program Committee. So ESA selected as a science theme in 2013 already, gravitation. Wanted to do gravitational wave, and this was the only proposal that addressed that science theme. Obviously, there was not no competition, and then we got selected in June, and NASA spoke up virtually immediately, hey, we are certainly interested in junior partnering with you and join that effort. So if you look at the project, ESA is obviously the mission lead. The way this works in Europe is they are responsible for the spacecraft, and then the payload is typically done by the national agencies, in this case led by a LISA consortium. So ESA is providing the mission lead, spacecraft, launch vehicle, some of the payload elements. The payload, most parts of the payload, and the science lead is done by the LISA consortium. These are funded by the European national agencies. NASA is a 20-25% partner right now, so the word junior partner. NASA provides more funding than all European national agencies for the payload combined, I believe. It might be at the same ballpark, right? But most of the money is coming at the end of the day from ESA. Here. So we are not a small member here. We provide key payload elements, spacecraft contributions, science and other support. It's the role of NASA, pretty big role, pretty great role. This is a notional schedule, right? You talk always about launch years, right? On some calendar, it's 2034, whatever that means, right? So we are right now here, the mid-phase A review, mission critical review. We just passed it. We got the email about 3 weeks ago, I think, that we passed the mission critical review. And now we can move on into the final review and going into mission adoption at 2023, 2024 timeframe, maybe late 2022. This indicates here December 2022. We were at one point scheduled for 2024, but it was pulled forward. One of the reasons is that we have 20 years of heritage developing LISA technologies, so we have a fairly good idea how to do that. We never started really from scratch here. And then production, we can go through the different phases. Production here of critical items starts somewhere here, payload production, and then launch 2023-ish, maybe late 2033-ish, maybe late 2032. There's a 1-year launch cruise phase in there. There's 6 to 8 months commissioning phase in there. So maybe 2034, 2035, we can begin science operations. Right? And the 10-year, 4-year nominal mission lifetime, extended mission, another 6 years. And about 12 years into the mission, the constellation will more or less fall apart. The distances between the spacecraft become too large. The velocities, relative speeds become too large. The systems will not be able to handle that anymore. There's a natural end to that mission. And we might run out of fuel steering the spacecraft around the test masses. That's the basic idea. In the US, we have another study office. Study scientist is Ira Thorpe at Goddard. The proto project hosted by Physics of the Cosmos program. GSFC, Goddard has a management, science and system engineering lead for the NASA components. It's responsible for telescope and laser development. JPL is involved, science and system engineering, interferometry, micropulsion systems. Marshall is involved. UF is doing the charge management development, telescope metrology, and we also do a little bit system engineering together in the ESA office there. Another LISA study team, appointed volunteers here, interface with the decadal survey right now. You know that the decadal survey is going on. Let me talk briefly about that. So decadal survey, LISA is part, official word is LISA is part of program of the record. That means the decadal is essentially, is not necessarily asked to rank LISA. It's not asked to rank LISA, but the decadal is asked to comment on LISA and provide guidance. And provide guidance could be an upscope, saying this is just the right amount of money NASA spending on this. And certainly I shouldn't talk about downscoping anything here, right, because that doesn't sound good. Right? But they are supposed to maybe upscope our initiatives here, our NASA contributions, or keep it at the right level, comment on this there. It's not one of the programs that will be ranked like LUVOIR and other missions that are going into the decadal survey right now for ranking. It's an ongoing mission. Same with Athena and WFIRST. These 3 missions are not ranked by the decadal. Okay, and this is a final sensitivity curve that I had already, and I'll stop here and wait for questions. Wow, that was an entire hour. Okay.
Thank you very much, Guido.